Good morning, pre-cal students. We're just going to hop right into it today and start talking about inverse functions. So our first example says f of x equals x plus 2 cubed plus 3. So this is our line f of x. So we're going to label that. Now we want to graph its inverse. So before we find it mathematically, we're going to graph it. The way that we do that is we need to figure out some points because remember the x and y for the inverse function are the opposite of the x and y of our original function. So let's go ahead and find some points on our graph. We cross an even point right there at -4, -5. So let me fill that in for my f of x graph. My x was -4 and my y was -5. All right, looking for another one. It looks like we cross again. Let's see here. Maybe at -3, 2. Here's another point. So we'll fill that in. -3, 2. All right, let's see. Looks like we also cross again right here at -2, 3. So let's fill that into our table. At -2, our function value is 3. And let's fill in one more so that way our whole table is all the way filled in. About -1 and 4. Okay, so now we want to graph our new function. Okay, but the way that we do that is we switch all of our x and y values from our original. So for our inverse, our first point would be at -5, -4. So again, I'm just switching my x and y's. To find the inverse. Okay, so the next one would be at 2, -3. Our next one would be at 3, -2. And our very last one would be at 4, -1. So now that we know all these points, we need to graph them. So our first point is supposed to be -5, -4. So I'm going to put a point right there. -5, -4. The next one should be at 2, -3. So putting my point at 2, -3. We have one at 3, -2. And our last one is at 4, -1. So now I have all these points, and I need to graph it so it looks like the inverse of our original one. Now remember, inverse means it's reflected across this line. That's why there's that black line in the middle at y equals x. So we need to graph it so it looks like it's a mirrored image of our red function. So I'm going to do my best. Okay, that's as good as my sketch is going to get. And remember that we could note that it's the inverse by doing f and that little -1 of x. So we have graphed our function and its inverse by using our tables. And as you guys can see, it is symmetric about that line y equals x. So that means if we were to draw diagonal lines right here, whoa, boom, diagonal lines go straight down to our new points. Diagonal lines go straight down all of our points are flipped across the line y equals x. So we are going to scroll down a little bit. We'll do this one in class. We're going to come right down here to does the function have an inverse? So scroll down when you're following in your notes. Okay, so if we graph the inverse of this red function, will our new function be an inverse function? So let's go ahead and quickly grab some points so that way we could flip our x and y values and graph this table easily. All right, so I'm going to have x and my inverse of my f of x. So let's do this one first because our point's at 0, 0. That's nice and easy. If we switch x and y, we still get 0, 0. All right, our next point we can use is negative 1, 1. So if we switch our x and y's, we'd have 1, negative 1. All right, and the next point, let's use negative 2, 4. So our new point would be 4, negative 2. All right, let's do the other side of the parabola as well. Our first point is 1, 1, which when you switch those two, easy peasy, 1, 1. Our next point could be 2, 4. So when we switch those, we got 4, 2. All right, let's graph this. Let's put our points, graph all these points. Ready, set, go. All right, we have graphed our inverse function. It looks like this. It's the blue parabola. It's like sitting on its side. And it's been reflected across this green line. So we know that this is the inverse of our original f graph. But we want to know if this blue function, if this blue graph is a function. So the way you figure out if a graph is a function is you want to know if it passes the vertical line test. And hopefully y'all remember the vertical line test. I'm going to write it over here. So for the vertical line test, if you could draw a vertical line through our function, it should only touch a function one time. If it touches more than once, it is not a function. So go ahead and pause the video so y'all can copy this stuff down. So I drew my vertical line through my blue graph. So it's a blue graph right here, and I can see that my pink line touches right here and right here. So that means that this is not a function. My inverse is not a function. The only way we could take the inverse of our original red graph is if we would restrict the domain of our new inverse function. Because if we took the inverse of f of x, we would have this top blue line, but not this negative blue line. So we would have to restrict the domain. All right, so let's see if there's an easier way to figure out if an inverse has a function without having to graph the whole new function. So let's scroll down and look at our second example. So our second example has a little table, so I'm going to zoom out. Okay, so here's our new function, for example 2, and here's the table giving us the points, so we didn't have to do like what we did up here. So for this one, we're going to see if there's an easier way to figure out if this graph has an inverse. The way we're going to do that is we're going to do a horizontal line test. So we are going to draw a horizontal line through the graph. That was a terrible horizontal line. We're going to draw horizontal lines through the graph and see, does that horizontal line touch more than once? That horizontal line only touches once. This horizontal line touches 1, 2, 3 times. meaning that this graph does not have a function, or does not have an inverse. Again, so you draw a horizontal line. If it touches more than once, you will not have an inverse of this function. So a vertical line test is to figure out if whatever you're testing is a function. Horizontal line test is to figure out if its inverse is a function. So take note of that, please. So make sure you take a note of the green things on the screen. So go ahead and pause the video before you move on. And my bad, this is actually different than that. So ignore that from earlier. This is going to be talking about mapping specifically. So here's a table with all of our x values and all of our y values. And we're going to try to figure out if this has an inverse. So we need to look at all of our y values, because remember, when we switch them, we're going to find the inverse. So if we switch these two, this would be our new x's, and these would be the inverse of x. And we can only have one x value per y value. So we're going to look at our f of x values, which would be our inverse x values, and see if it repeats. We can clearly see it does repeat. Since it repeats, it will not have an inverse. This means it would fail the horizontal line test. It has more than one y value, so that means it will not have an inverse function. More than one matching y value, I'm sorry. So there's 7 here and there's a 7 here. So it will not have an inverse function. So we're going to do one more part right here. The one-to-one passes the vertical and horizontal line tests. Make it bigger. There we go. So first we're going to look at mapping, and for some reason my picture didn't copy over, so I'm going to go ahead and draw that quickly, and once it is on the screen, pause so you can copy it down. So what does it take for a function to have an inverse without domain restrictions? So for these ones, we would have to have domain restrictions or we wouldn't have a real function. So we want to know, what do we need to happen so that way we don't have to have domain restrictions with our inverse function. So if we're looking at mapping, which is like our table or these circles, this would be our x values, these would be our y values. We want each x to go to its own y value. You do not want a double arrow. If you have an arrow, 2 arrows coming out of that 2, that means it would not be, its inverse would not be a function. So you want each x to go to its own y. All right, for graphs, we want it to be 1-to-1, which means that there's only going to be one x function or one x value for every y value. So it could look something like this. Let me redraw that real quick. Hold on. So we could have something like this, where it's going up and up and up, and there's only one x value for every y value and only one y value for every x value. So as we can see with this blue one, this blue line is always increasing, and this red line is always decreasing. So these both pass the vertical and horizontal line tests, which means that we would have an inverse without restricting the domains. So what does it take for a function to have an inverse without domain restrictions? When we're mapping each axis to go to its own y with no double arrows, it should always be increasing or always decreasing. That way it passes the vertical line test. So you go like this, passes a vertical line test. No matter where you draw a vertical line, there's only 1 point. We also wanted to pass the horizontal line test. No matter where you draw a horizontal line, it'll only touch 1 point, and that tells you if your inverse will be a function. We'll finish the rest of these notes next class. Have a super great day. Bye, y'all.